parametric mode. So parametric mode, I'll show you on my screen as well, once the calculator decides to go. So this is, I think, will probably be a new mode for all you guys. So you go to mode, and you guys see down below it says function, and then off to the right it says parametric, polar, and then SEQ. So I think, if I'm right, for most of you, if not all of you, you have kept that on function every time, like I think for all your classes. You might have done polar, that makes sense, you've done polar, but maybe not parametric or sequence. So we're going to actually end up doing all of these at one point or another. Today is parametric. So if you would, go to parametric mode, and looks like that. Hit enter on once you get to that point. And then here are some instructions. It says, start with an example from first semester, and see if you can follow these instructions. I'll maybe just kind of quietly do this up here. See if I can get split screen as best I can. So this time when you hit y equals, you get something you've never probably seen before. It says x1 of t equals y1 of t equals. So you have some instructions up there. Follow those instructions. I'll do the same. Did you notice when you hit the xt theta n, it does not show up as an x anymore? It shows up as a t. And then the next instruction is about highlighting the slash and pressing enter. I don't know about pressing enter twice. You want to get like the little, instead of a slash, you want like the little ball, little open circle looking thing. Yeah, I think some of the newer things, so yeah, so yep, you scroll. I'm going to stay with that. Then go to your window and set your Tmin and max there. So Tmin 0, Tmax 30. And hit graph. What's what? Just leave it as is. I think it defaults at 0.1. So when you guys did that, did you get essentially like a ball just kind of sliding back and forth? Yeah. So I labeled this as like an example from first semester, like from top A, B. These are all the questions that start off with a particle is moving back and forth along the x-axis. That's what this is. You see the particle moving back and forth along the x-axis? Does that make sense? And so, some of the questions that could be asked of you would be, what is the velocity of the particle when t equals 2 seconds? What's the total distance traveled by the particle? What's the displacement when t equals 3? Whatever. Does that make sense? All those questions sound pretty familiar. What we're doing, but sound familiar? Okay. So what I would ask you to do here is those next couple of steps, and I use the highly technical words of mess around with the T step and see what happens. Mess around with the Tmin, Tmax and see what happens. I'd say just kind of play around with it for a couple minutes. See if you can figure out how those things affect the graph. Just love to hear what you do and what you see. What'd you guys do with your T-step?
You change the speed of the
0.6, say again?
doesn't it change the speed?
Change the speed, okay. So Josh, so Alex made his 0.6. What'd you do with yours?
When I put it at 0.1, it was slower.
Okay, what was it before?
0.13.
Okay. Let's see what 0.6 looks like. Anybody do something different with their T-step?
I did 6 just now.
A 6.
I plugged in 15.
Okay, so here's a T-step of 6. Right? So it does seem to affect the speed, right? Okay. Did anybody make the T-step pretty small? Yeah, like if you do 0.01 or something, then the ball, it's moving, but barely. Oh man, it'll take forever. It's still going. So, hey guys, I do have a question for you. Based on fiddling around with the T-step, does anybody have any idea of what that is? It does affect the speed, and it does have to do with an interval of time, more or less. Sure. Yeah. Yeah, Johnny, what do you think? That's good.
Is it familiar, or is it similar to the, I forgot what it's called, the equation though, we have like the T, like each step from like, when you have the x, 0, x, 1, x, 2, x, 3.
Oh, with Euler's.
Yeah, is it familiar?
It's actually a similar idea, I would say. Yeah. So think of it like this. Think of your T-step as this. Like if I, I think this will really help you get what this is doing. If I asked you, it's funny, Alex and I were having this conversation. If I asked you guys to graph a function by hand, like paper and pencil, no calculator allowed, and let's say that you decided to plug in some values, right? Input, output, so on and so forth. And let's say that your domain was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wouldn't your graph look potentially very different than if your inputs were 0, 0.1, 0.2, 0.3, 0.4, 0.5? Or what if you wanted to be really precise, or more so, and instead you went 0, 0.01, 0.02, 0.03, 0.04, 0.05? That if you really tightened up the interval on which your inputs were, I think that would eventually make your graph look better and better. Think of the T-step as the length of time between dropping a point onto the graph, or if you think of like a breadcrumb trail. So, like, couldn't you think of like plotting points to graph a graph as like dropping breadcrumbs, like dropping little points? So if I was going to draw a graph based on the path that I'm walking, and I'm like dropping a breadcrumb, so on and so forth. Can you picture these breadcrumbs on the floor? Wouldn't these represent my path? These little breadcrumbs, okay? So if my T-step is like 0.1, that would be me like dropping breadcrumbs like this. Like I'm just like dropping a breadcrumb very quickly, every like 10th of a second, let's say. I'm dropping a lot of breadcrumbs here. But if my T-step was bigger, like 1 or 5 or 10, that would be me doing this, breadcrumb. Breadcrumb, right? And so the bigger the T-step, the longer the space between the breadcrumbs being dropped and the points being graphed. Would it be fair to say that the bigger the T-step, the less accurate the graph? The tinier the T-step, the more accurate the graph, more precise, right? You can see the path followed better. That's really what it's about. It's about how many breadcrumbs you want to drop. And so that's why speed seems to be affected, right? If you're only going to drop 1 or 2 breadcrumbs over the course of your 30 seconds, it's just going to be like, bam, bam, done. But if you're going to drop 10,000 breadcrumbs over the course of your 30 seconds, it's going to take forever, right? To like record all those little points that you've been dropping down. That's why the speed seems to be affected as well. Did you guys mess around with the T-min, T-max? What does it seem to do, Josiah?
I mean, I didn't really do a whole lot of it. I just changed it to 60.
Okay, so when you moved from 30, you did 0 to 30, and then you did 0 to 60, what seemed to happen?
Like, if I made the step size bigger, it would still go like the same speed.
What if you kept the step size constant and only expanded your T max?
I changed my T-max to 2 at one point.
Yeah.
And it stopped sooner.
Yeah.
When it did 30, is it the amount of time that it goes graphing?
It's the amount of time that it spends graphing. Yep. So yeah, so if you did,
When it's at 60 instead of 30, it just goes slower.
well, I think it just goes longer.
Yes.
So this is my step size at 0.1 for t equals 0 to 30. So it's going to go for just a little while here. But if I then take my my t min max to go 0 to 60, it's just going to go for twice as long, right? So this is 0 to 30, and if I do 0 to 60, like if we put a stopwatch on it, we could probably see that this thing will just go for twice as long, simply because I've kept its t step the same, and it just keeps going back and forth, back and forth, back and forth, back and forth. Anyway, okay. So again, I just want to bring up the idea that this is very much A/B stuff. You've got a particle moving left and right on the x-axis. Any ideas of how you could get the particle instead of moving left to right? You just get it move up and down on the y-axis? What could you do? Yeah, make the x 0 and the y 5 cosine of t, right? That would turn it into this instead of this. Yeah? Okay, so we've done lots and lots of problems like this. Before we go here, why don't we move into the two-space world, 2 dimensions. So take a look at the next bullet point here. So to change from 1D motion, instead of a particle just moving left and right or up and down, we can make it go to 2-dimensional by making y1 something other than a constant. So keep your x the same, go back to your y equals, keep your x the same, but now I'm suggesting that we make y1 natural log of t. So when you do this, no longer is the y-coordinate just going to stay 0 the whole time. The y-coordinate is allowed to change and go up or down or whatever. And so this time when you graph it, you get something like this.
Wait, Alex's is doing something completely different.
What motor are you in?
We're all 3 getting something really different. Oh wait, no, Brandon, mine's gonna be yours.
This looks like a T-step. So his T-step is 1. What's your T-step? This goes probably an off and stuff like that.
At LMT.
So Alex is like, what is he?
Yeah. Oh, you said
I've got it as circle line. So it records the circle as well as the path. So, hey, can you guys see still that this particle is going left and right? Just like it was doing before? But now not only is it going left and right, it's going up and down, or technically just up on this one, right? So when you make that y of t something other than a constant, well now the y variable can increase or decrease, or do both at different points in time. and therefore release the go to that. And again, this is something that you can very much play around with. You can still mess with your T-step and your T-min, T-max, and that'll, lay down more or fewer breadcrumbs. It'll allow it to go on further or shorter times. You can also just play around with this in general. I mean, like I really honestly love and think that it's beneficial for you to ask questions like, well, what would it look like if I left the x at 5 cosine t, but what if I wanted to make this t squared? What would that look like, right? So I just decided to change, and it does something like that. It kind of raises off the top of the graph. So you can do all kinds of just experimenting with this and just kind of, I guess, seeing what affects what. And I think this is a good jumping off point for what parametrics are. I will say this, it's at this point, usually someone will be thinking, and maybe they've noticed that these are called, maybe they've heard or seen this, these are called parametric functions. And I think that they would rightfully ask the question, hold on, how is it that we can call these parametric functions when you get some graph like this, whoops, with an error? How can you get some graph like this and call it a function? Like, it's not passing the vertical line test, is it? Right? So here's where we start to expand our knowledge of what a function is. It's obvious in this case, y is not a function of x. Right? You can see it right there on the graph. But y is a function of t, and x is a function of t. In other words, for every input of t, there's only one y value. For every input of t, there's only one x output, if you will. And so x is a function of t, and y is a function of t, but y is not necessarily always going to be a function of x. That's why you can still call these functions, even though the y and x graph doesn't pass the vertical line test.
So is the calculator really twice as hard? So like instead of x just being 0.00,
it's t's. The t's are the inputs. So it's like, I guess so, right? Because it's saying t is all these inputs, and then you're getting an output for x and an output for y, and that's giving your xy points. Hey, one last thought to leave you with, real simple. Like, this opens up your world a little bit, and we'll continue to do this next week. Just keep in mind that if you ever do end up taking a calculus 3 class, there will be an x of t, a y of t, and a z of t. Because not only will the particle be moving left and right and up and down, it will be moving towards you and away from you all at the same time. It's 3 space instead of just 2 space. That is a topic for another class, of course. So, anyways, hope you guys have a good day. I will see you tomorrow.